Okay, so today I would be talking about, first of all, I'm Salman Sheikh, D1 student, and I would be talking about today distance-based outliers. Here's the contents of my talk today. That first of all, I'm going to define what is an outlier and some of the statistical models of outlier detection. And then what is the distance-based based outliers and some of the techniques, major techniques given by previous authors, Noor and Ramaswamy. And then finally, distance-based outlier, a very short description of our work and what I'm currently working on in the references. So first of all, starting with the definition of outlier. So an outlier is a set of data. An outlier in a set of data is an observation or point that is considerably dissimilar or inconsistent with the remainder of the data. And it is defined by Stephen Hawkins in another way, like an observation which deviates so much from the other observations, so as to arouse suspicions that it was generated by a different mechanism. So there are several definitions of outlier that is actually given by different authors. If you look at this particular image, so we can say that observation or the object O1 or this group of objects and this particular object O2, they are outliers because they are like in the lower density region, or they are far away from the majority of objects. Similarly, if you look at this particular sequence of this particular signal, so this particular signal is uniform like this, but it's anomalous over this particular region. So we can say it's an outlier or an anomalous sequence. So there are several applications of an outlier. So it has been said that one person's noise is another person's signal. So for some application, the rare events are more interesting than the common ones. Like in credit card fraud detection, we are interested in finding the unusual pattern of transactions. Similarly, in telecom industry, we are looking for the customers who are not usual, or like they are using a lot of, or they are generating a lot of bills, or they are using, or we can say like they are heavy users of our bandwidth, like. And similarly, in weather prediction, we are looking for some rare events or some rare weather. So outliers are actually the rare events or the unusual things that are some of the applications of outliers. In the theory of statistics, there are several models available for finding the outliers. And up to over 100 discordancy or the outlier tests have been developed for different circumstances. And these all tests or outlier tests, they depend on the different types of data distribution, like normal distribution, t-distribution, student distribution, or whether or not the distribution parameters are known, and the number of expected outliers that we are interested in, and the type of outliers like upper outlier or the lower outliers. So although there are hundreds of outlier detection techniques available in a statistical model or statistics theory, but there are some problems in statistical techniques, that almost all of the statistical techniques are univariate. That is, we cannot model our multidimensional data using those statistical models, and sometimes we don't know the data distribution of our data, and we need to take care of, and we need to use some of the tests to confirm that our distribution, like in case of normal distribution, we need to check whether the distribution is normal or not by using skewness or kurtosis tests. Similarly, parameter of distributions may be sometimes difficult to determine. So these are some of the problems in statistical techniques which are responsible for their limited usage in computational sciences. So in order to overcome these problems that were in statistical techniques, some of the following major distance-based approaches for outlier detection are proposed in computational science, which are based on nearest neighbor-based or density-based or clustering-based. And the distance-based approaches for outlier detection is actually very common because it scales nicely to large databases and are relatively non-parametric as compared to statistical models and can handle high-dimensional data.
What do you mean by relatively non-parametric?
Like relative to statistical models. Like statistical models, they require a lot of parameters, mean, variance, and like this. But the distance.
Mean and variance.
Yeah, like in case of
distance-based outlier detection, you need to give some 2 or 3 parameters.
Yes, some of the parameters, but not as much as in case of statistical techniques.
This statement is not so correct. I think if you say non-matter parametric, no parameters are given.
But not that type of parameters that we normally have in statistical techniques, which are difficult to determine.
If you want to say that the number of parameters is small, then you should say so. Relatively non-parametric does not make any sense.
Smaller, we can say the parameters are easier to find out in case of distance-based outliers. But in statistical techniques, like we have to perform a lot of calculations and then we find out our parameters.
Yeah, so if you intend to say so, you should write like that.
Makes sense. So, one of the very famous outlier detection techniques, technique is distance-based outlier by Knorr, which was given in late 90s, and according to this particular definition, an object O in a data set P is a distance-based PD outlier if at least fraction P of the objects in T lies greater than distance D from O. So, like these are the data points, and if from this particular data point, if there are P or there are a P percentage of data which is outside this particular D distance of this object O, then we can call it an outlier. Or in other words, we can say if there are less than M percentage of data points within this particular radius D of object O, then this particular object is considered to be an outlier according to this particular definition. So with this definition, or with this notion of outliers, authors gave 2 algorithms: the nested loop algorithm, with the complexity delta n square, where delta is the number of dimensions, or the cell-based algorithm with the complexity OC power delta plus n, where C is some constant that depends on the dimensions, number of dimensions. So the nested loop algorithm is simply calculating the distance between every 2 data points, like calculating distance between this point and rest of the data set. Similarly, taking another point and calculating the distance between rest of the data sets. So hence we are having a very high complexity that is order of n square. So I will just talk about cell-based approach, which was given by Knorr, that to find distance-based outlier for, like I'm talking about first 2-dimensional data. First of all, we need to quantize each of the data objects onto 2-dimensional space. And we have to quantize in such a way that the space is partitioned into cells of length D, which is our diameter that we have just seen over here, this diameter. That the length of each particular cell is D divided by 2 radical 2. And the diagonal is 2D by 2, such that the 3L or the 3 length is greater than the distance D, or the radius D. And the cells colored red are actually the L1 neighbors L1 neighbors of this particular cell CXY, and cells colored blue are actually the L2 neighbors. So this is this is actually the definition given in by Nor, that objects that in L1 neighbors are guaranteed to be within the distance of CXY, within distance D of CXY. So all the objects that lie in this particular layer, that L1, or the red layer, or the layer with red, so they are guaranteed to be within distance D or the radius D of CXY, or this particular cell under consideration. Similarly, objects that are outside L2, that is this particular layer, blue layer. So objects outside L2 are guaranteed to be greater than distance, greater than D distance from CXY, and they are if we are having greater than distance D with respect to CXY, then all the objects within this particular cell would be outliers. So using that particular definition, if there are more than M objects in L1 neighbors of CXY, then none of the objects in CXY is an outlier. Where M is like threshold, we can say it's a threshold, and it depends on total number of objects in our data set, 1 minus P, where P is the fraction of objects that is one of the parameter of this particular algorithm. So if there are more than M objects within L1 neighbor of CXY, then none of the objects in CXY or this particular cell is an outlier. And if there are at most M objects in L1 plus L2 neighbors of CXY, then all the neighbors in CXY are outliers. So if we are having like equal M objects by combining this one and this layer, that L1 and L2 layers, then this particular, all the objects within this particular cell, it is said to be all the objects would be outlier. But if the third condition is if there are more than M objects in L1 plus L2 neighbors of CXY, then CXY may or may not contain outliers. And in order to find that whether they are outliers or not, we need to calculate the distance between all the objects within CXY and the L2 neighbors. And by calculating the distances, we can find whether the objects within CXY outlier or not. But by using cell-based approach, we can prune out a lot of our data points or a lot of our data objects, and in majority of cases we are able to find that an object is not an outlier by using some cell-based approach. But if we are unable to find, then we need to calculate this individual distances for each and every object. So, as a comparison of cell-based and nested loop algorithm in this particular paper, we found that this particular approach, or the cell-based approach, is only suitable for 3 dimension or up to 4 dimension, but not more than 4 dimension. As we are moving more than 4 dimensions, the time taken by cell-based approach is far greater than nested loop, because the number of cells increases exponentially with the number of dimensions. So the time taken by the cell-based approach is quite higher as compared to nested loop algorithm, but it is only efficient in case of 2-dimensional, 3 or 4 dimension. So there are some certain shortcomings of cell-based algorithm. That first of all, the cell-based algorithm, it requires a distance d, which is difficult to determine, and we have to decide by ourselves that depending upon the scenario, that what should be the distance d. There is no way to calculate the distance d. It depends upon the application. So, and it also does not provide ranking for the outliers, whether the outlier is a strong outlier or not so strong outlier. And also it does not provide scaling for a higher number of dimensions, like we have just seen that it is possible to calculate efficiently outliers up to the 4 dimension only. So to address the above mentioned shortcomings of cell-based algorithm, Ramaswamy gave new definition of distance-based outliers. And according to this particular definition, given an input data set with n points, parameters n and k, where n is the number of desired outliers and k is the kth nearest neighbor of the data point under consideration, a point P is a distance-based Kn outlier if there are no more than n minus 1 other points P dash, such that dkP dash is greater than dkP, or we can say this dkP is the distance of kth nearest neighbor from point P. So again, if you look at this approach, like for the naive approach or the nested loop algorithm, for this particular approach, we need to calculate the distance between each and every point. And now if we are assume that k equals to 2, means kth nearest neighbor, or the second, and we are interested in only 2 outliers, n equals to 2. So n equals to 2, this is k equals to 1, or the first nearest neighbor, and this is the second or the kth nearest neighbor. So we are actually interested in kth nearest neighbor only. So we have found this is the kth nearest neighbor or the second nearest neighbor of this particular point P. Similarly, we are going to calculate for other points, and we found that this is the kth nearest neighbor or the second nearest neighbor. And similarly, we are going to calculate for all other points, and finally we are going to find that these 2 points are outliers depending upon their kth nearest neighbor distance, because the distance of their kth nearest neighbor is highest among all other points. So with this notion of this particular definition, outlier, author has given 2 approaches of outlier detection. One is index based and another is partition based. So before moving towards index based approach of outlier detection by Ramaswamy, I want to define MBR, or minimum bounding rectangles. Minimum bounding rectangles they are actually using for approximating the set of points and to prune the search space. So by computing the lower and upper bounds on dkP, or distance of kth nearest neighbor from point P for points in each MBR, entire MBRs can be pruned that cannot contain outliers, and this will dramatically reduce the number of distance calculations for distance-based outliers. And besides this, we would be using the following notations for calculating distance between a point and MBR and between MBRs. Okay, minimum distance between a point and MBR R, and similarly maximum distance, similarly minimum distance between 2 MBRs and maximum distance between 2 MBRs. So I would be using these notations and this MBRs in the index based algorithm. So index based algorithm is actually using a special index R star tree is used for storing the data points. And how actually the pruning is done, the major part of this index based algorithm is pruning, that assuming that let dkP denotes the distance of kth nearest neighbor of a point P for a subset of input points. So for the points seen so far, this is the dkP distance. Now if minimum distance between this point P and MBR is greater than dkP distance or kth nearest distance of point P, so none of the points in the subtree rooted under the node MBR will be among the k nearest neighbors of P, and we can actually prune the entire MBR, because this MBR may not contain any of the nearest neighbor points, because the distance is higher than the already found kth nearest neighbor distance. So we can prune the entire MBR. Similarly, we are going to perform this test for the all other MBRs, and we can prune a lot of MBRs, and we can prune in other words a lot of search space. So pruning entire MBRs results in improvement in execution time for index-based algorithm. So this is a very simple index-based algorithm, and the main part is the pruning, and they are pruning the subspaces by using this particular notations.
So is this technique proposed by the original?
Because I'm using this. I have introduced two techniques. This is the technique by Ramaswamy. This is another paper. This is the paper in Sigmode, 2000.
They already proposed index-based algorithm.
Yes. Another approach or another technique that was proposed in this paper, that is partition-based algorithm for outlier detection, and in this approach they are actually partitioning the whole space into smaller partitions, and then they are, or in other words we can say they are clustering their whole subspace, or they are clustering their whole space, and then they are performing the outlier detection. So again we would be using bounds for partitions, and using those bounds we would be pruning the entire clusters or entire partitions, and this is going to like reduce a lot of our execution time. So starting the first step of this particular algorithm. The first step of this algorithm is generating partitions, and for generating the partitions they have used Birch algorithm, and Birch clustering algorithm is a very common algorithm for generating partitions, and it generates uniform size partitions, and the time complexity of this particular algorithm is linear, and it simply scans the whole of the data set only once. So Birch stores a compact summary of each clusters in a tree structure, or the CF tree structure, and for each successive points it traverses the CF tree to find the closest cluster, and if the point is within a threshold distance of the cluster, it is absorbed into it, otherwise a new cluster is formed. So in this way only one scan is required for generating this CF tree, and in this work each partition is actually represented again by the MBR, or the minimum bounding rectangle for its point, and in other words we can say that each and every cluster is actually represented by an MBR, or minimum bounding rectangle, and again MBR would be used to prune the search spaces. The second step of the same algorithm, that computing bounds for partitions. Now for identifying the candidate partitions, because in the first step we have partitioned our whole data set, and in order to identify the candidate partitions PC, the bounds P lower and P upper needs to be computed, and P lower and P upper are actually computed such that P points such that for all P belongs to partition P, P dot lower is less than K nearest neighbor of point P, and it is K nearest neighbor of point P, the distance of K nearest neighbor of point P is actually less than P dot upper, and P dot lower and P dot upper is actually determined by finding the L partitions closest to P, means all the partitions that are closest to P, such that the summation, the total number of partitions, they must contain greater than K number of objects. So this is the condition, that they should contain at least K number of objects in them, and hence we can find the P lower or P dot lower is minimum distance between partition P and the farthest partition among L partitions. So we are finding actually the distance between MBRs, and similarly the maximum distance or the P dot upper is actually calculated by calculating the maximum distance between partition P and the farthest partition among L partitions. So for each and every cluster we are actually calculating this P dot lower and P dot upper, these values, and these values would actually be used for pruning the partitions.
So do you make distinction between big P and small P?
P is actually P is in the big P is the partition, and the small p is the points within the partitions. So for all points that belongs to partition P.
For identifying the candidate partition PC. Is it correct to say that you are going to judge that given single point is outlier?
Actually, right now in this step, in the first step, we partitioned the whole space into smaller partitions, or we can say several MBRs, and then we are calculating the lower and upper bounds for each and every partition.
Bound in what sense?
Bound for each and every MBR. Let's say, like we have calculated so many partitions. Okay.
Rectangles.
Yeah, because we are using MBR, so minimum bounding rectangles, you can say. So within each partition, we are having these are points P that belongs to partition P. Okay, and here we are actually determining the lower and upper bounds for this particular partition, and this is actually determined by because maybe the nearest neighbor. Let's say there are some overlapping MBRs, so the nearest neighbor for this particular point may exist in some other partition, so or in some other MBRs. So one of the condition is that the total number of points within L partitions that we are taking under consideration to find the P dot upper and P dot lower, it should be greater than K. So it is possible that in a single partition, let's say if K equals to 50, so in a single partition we may not have all a total number of like K number of points. So we need to consider 4 or 5 partitions in order to calculate the K nearest neighbors or P dot lower and P dot upper for a single partition. Actually, first of all,
P alpha is determined without any assumptions. I mean, if you take one point, then you can calculate the distance. Then you can decide the upper bound and lower bound. That makes sense for me. But you said that at this moment you don't have any. You don't have decided any point.
Right now,
my question is simple. What is the bound in what sense?
Bound
from which point? In what sense?
Actually, we are calculating the bound for each and every point within a partition P. Okay. Within a partition P, we are calculating the bound for each and every point, and
yeah. So that is what I'm asking. You take one point, then you can calculate some bounds. Is that right?
Yes, for each and every point, yes. in a single partition for each and every point P, we are actually calculating the bounds.
Okay, okay. That is what I'm asking.
Okay. Because it was stated over here that for all the P, actually I have not written that P is a point or that belongs to partition P. So for all the points P that belongs to a partition, we are actually calculating the P dot lower and P dot upper with the help of them.
But these two P must be uppercase.
Yes.
P lower and P uppercase.
Yes.
But in the second calculation, you don't consider the cardinality of P. So P may contain some number of points. So why you can say that mean this calculation gives, for example, P's lower bound.
Lower bound.
Yeah, for example, P itself may contain more than K points. Here, in calculation of P1 to PL, you exclude P itself.
In this case,
Yeah.
among L partition. So this P is the part of this group, like it is within L. You can see.
But the P is excluded. The number of points included in P is not counted when you decide P1 to PL. So suppose that capital P contains some points or more than K points. So the case nearest neighbor may exist inside P. So in that case, this lower bound is not correct.
Then in this case, this would be within a partition, like P comma, this would be like, it is also possible to calculate P comma small p.
I don't understand what you're saying.
What Kitawa Sensei is asking is that you should use sigma rather than, I think.
Sigma.
So something is something is not natural or not reasonable. Mean list P, farthest partition among L partitions, but for example, P itself contains many points. K's neighbor of some point P inside capital P may exist inside capital P.
Yes.
In this case, this mean list is not lower bound. So intuitively something is incorrect. Yeah, some constraints or some conditions or something are missing, I think.
Okay.
I read this paper many years ago, and at that time I got the point, but this formula looks strange.
Maybe because I comprehended myself, so maybe I have made some mistake.
でもそれでも P のだって P の K 分別ネイバーラージ P の中にある可能性があるそれでも変だよだから P1 から PL の中で P も含むのかクローデスと P 含むなら必ず P が入ってるから そう書くはずだよな。そう書いてないとしょうがない。いや忘れたけど、まあなんかちゃんと元の道具にはちゃんと書いてある。
Shall I continue?
Something.
Yes, something. Because the algorithms.
I cannot get the point. Okay. After calculating the lower and upper bounds, now we are moving towards computing the candidate partitions. So we are going to prune the partition by identifying the candidate partitions that potentially contain the outliers. So candidate partitions are those partitions that may contain outliers, while rest of the partitions we are going to prune depending upon their lower and upper bounds. And the first step is to estimate the minimum decay distance. And minimum decay distance is the lower bound on decay for an outlier. So decay is actually the distance of the kth distance of all the outliers found so far, and this is the approximate distance because we have just taken some of the records and we have found decay, and depending upon this decay we are going to calculate find that whether a partition is a candidate or not. So let P1 to PL be the partitions with the maximum values for P dot lower, such that the total number of points within the L partitions is greater than N, where N is the number of desired outliers. Then minimum decay distance, or this value is the minimum of all the lower bound of all the partitions which are which are within L, like within L partitions. So in this way we are going to calculate the minimum decay distance, and we are actually pruning the rest of the partitions depending upon this minimum decay distance. So partition P can only be a candidate only if the upper bound of this partition P is greater than minimum decay distance. So minimum decay distance is actually, we can say, the lower bound of our outliers, and a partition can only contain outlier if the upper bound of this particular partition is greater than this particular distance, and that would be added as a candidate set into this candidate set of outliers. In the final step, after identifying the candidate partitions, index-based or nested loop algorithms can be used to find dkn, or the kth nearest neighbors of n or n outliers depending upon the distance of kth nearest neighbors from the candidate partitions only. So finally, comparison of nested loop and index-based and partition-based algorithms. Here, by varying the data set, we found that partition-based algorithm is performing best, or it's taking the least amount of time, even if we are increasing the data set size. Similarly, by varying the k or k nearest neighbors, and by changing the size of, by changing the number of partitions within the, by changing the partition-based algorithm, again we found that partition-based algorithm is performing well as compared to index-based algorithm. And finally, by changing or by evaluating the same for the different number of dimensions,
we found that partition-based algorithm is best among the three approaches that he has given. Okay. Finally, I would discuss something about distance-based outliers in uncertain data, that is our current work. So in our work, it is the extension of Node's idea of distance-based outlier detection, and here we are assuming that the object A, object U is uncertain under normal distribution. So we are assuming that the points or data objects are uncertain, and the uncertainty is under normal distribution, and we know that under normal distribution higher concentration is of the point is at the center, and as we move away from the center, the concentration or the probability becomes lower and lower up till infinity. So hence we can define the distance-based outlier for normally distributed data points, that an uncertain object U in a data set T is a distance-based outlier if the probability that objects O belongs to T exists within distance D of U is at most M, where M is actually the threshold depending upon the number of objects in our data set, and P is the fraction of our data set. So where N is the number of objects in data set and P is the fraction of objects in T, and objects O are all normally distributed.
This statement is it's a rather strange because if the probability is at most M, it's strange. Probability is at most M. That will not.
This is our threshold, we are calculating.
Probability value takes from 0 to 1.
But we are summing up the probabilities. Yes, we can't say that probability. And the summation of probability.
Summation.
Because we would be summing up the probability for individual objects and their P.
The expected number of neighbors.
Expected number of people.
So anyway, this statement is
Yeah,
correct.
So can we say that if the summation of probability the objects, because we are summing the individual probabilities by calculating the probability between two objects, and then we are comparing it with M or the threshold.
That's the expected number.
Expected number. Okay. Okay. So, for distance-based outliers in uncertain data, in 1D case, since the distribution of normally distributed data points is given by this particular expression, probability that the uncertain object U exists within distance D of another uncertain object B of x2 is actually given by this particular expression, and this expression is actually simplified using a standard normal variable to this particular case. Similarly, for 2D case, the two-dimensional probability, the two-dimensional normally distributed function is actually given by this particular expression, and if we are taking the same approach as that in case of one-dimensional case, So probability that the uncertain object in two-dimensional U exists within distance of d of uncertain object V is actually given by this particular expression, and in this case this would be simply the multiplication of two probabilities, this one. I checked it and this one is last one.
You are just concatenating the formula for one dimension.
No, there is a complete derivation available for, like, I derived this and I found this, and I checked both they are giving the same results.
This integral is not correct.
Integral is not correct.
Because you are measuring the distance by Euclidean distance, right? If you calculate the distance by Manhattan distance, it may be correct.
Anyway, we took the same approach, the same.
In one-dimensional case, it's correct. It's correct, I think. But you are just calculating the multiplying the formula for the one-dimensional case
into two-dimensional case.
In the two-dimensional case, the distance is calculated by Euclidean distance. So this integral is not correct. I think that this integral is correct, then you can derive the last formula. But this integral is not correct.
So Euclidean distance, you think this exponentials?
No. You 2 points must exist within the distance d. This condition does not correspond to this integral.
These bounds.
You are just to calculate the bound for x-axis and y-axis. Incorrect. I advise you to consider the polar coordinate.
In polar coordinate, I was unable to incorporate like these means, so they were making some trouble. Okay, I'll consider that again. Okay. So finally, I am still working on some pruning approach for evaluating the distance-based outliers to reduce the number of probability calculation, and also looking for the extension of proposed distance-based outlier detection for more than 2 dimensions or 2 dimensions. That's it. Thank you.
So you should derive the correct formula using polar
Coordinates.
Yeah, of course, it should just depend on the parameter b. And irrelevant is the dimension of the point. So anyway, yeah.
So polar coordinates like that would only be using 2 integrals instead of 4.
I don't know. The 4 integral will be necessary, I think. Even if you polar coordinate, of course, two coordinates.
Yes.
Polar coordinates. Distance on the angle.
So again we would be having like
So you need to
R1
integral both for the angle and the distance.
So R1 theta 1 and R2 theta 2 again. So there would be like 4.
Anyway, the formula is not correct, then you cannot consider anything.
Okay. So, any questions?
はい、何かはい、じゃあ